So what changed in the new millennium? Well, companies like Google and Amazon started to store unstructured and semi-structured data, such as web pages and book information. And we learned earlier in the NoSQL lecture that this has led to the development of new data models outside of the standard relational ones that we learned about. And as we learned earlier, scaling up relational databases in general is hard due to consistency concerns. So while the various NoSQL data models, such as document stores and key value stores, were developed, MapReduce was also proposed around the same time as a way to interact with such data models in a parallel fashion. Before we talk about how MapReduce works, however, let's first discuss how data is stored in the MapReduce system. We already learned about storing unstructured and semi-structured data on a single machine. And we also talked about sharding and replicating them across multiple machines. MapReduce assumes data is stored in a similar data model. It aims to store terabytes to petabytes of data and organizes data into chunks of a few megabytes in size. Each of these chunks is replicated for fault tolerance across multiple machines, just like what we have discussed before. Google first implemented its distributed MapReduce file system called Google File System, or GFS for short. And this was followed by an open source implementation called Hadoop File System, or HDFS. Now, MapReduce itself was proposed in a paper published in 2004 by Google folks, with a subsequent open source implementation called Hadoop. As I said earlier, MapReduce is a programming model that targets interaction with such semi or unstructured data that is stored across many different machines. So, MapReduce is originally designed to solve problems that require reading a lot of data. For instance, reading all the web pages out there in the web, in the case of Google. It breaks down the problem into 3 steps after data has been read. First, map, which extracts information from each record or document that we have read. Then, based on the extracted information, we shuffle those records and documents across the machines. And then we reduce the shuffled data, where reduce here means some form of aggregation or summary. And we finally write the results back to the disk at the end. The idea here is to keep this 4-step paradigm the same for all problems, but we change the implementation of map and reduce for each of them. This is actually very similar to SQL, where we decompose each query into select, from, and where. Each query remains structurally the same, but its select, from, where clause would change. In GFS and also in HDFS, we assume that data is actually stored in flat files, not relations, where each file is simply a bunch of key value pairs. And as I said, a MapReduce program then reads in these key value pairs and outputs one or more of these pairs, with the output key here at the end being optional. For instance, if we want to count the total number of pairs, then we really don't care what the output key itself is. After reading in the data, we run the mapper program, or the map phase. The mapper program is provided by the user, where it takes in a bunch of key value pairs and outputs one or more of key value pairs. Here, the key and value in the output can be completely different from the input in terms of their types and obviously also their values. The interesting point here is that the map program is assumed to not keep states across multiple key value pairs, so that the system can run the mapper on each of the input key value pairs in parallel. This won't work, for instance, if our mapper function stores some sort of intermediate state, such as a count or an aggregate, for all the values of key values pairs that it has seen. Because in this case, we will be storing states across multiple input key value pairs. And after the mapping phase finishes, the system then groups together all pairs that have the same key value. Each such group is then passed on to the reducer phase. Like map, the user provides an implementation of the reducer. Here, the reducer takes in a bag of values that share the same key, and it outputs one or more values as the final output, with again the key being optional here. And like the map phase, the reduce phase can also be run in parallel, with a machine or a worker thread processing a single group of values that store a common key. Let's go through an example to see how this works. Suppose we have a large number of documents, and we want to count the number of occurrences of each word within those documents. Let's assume that each document consists of its key being its document ID, and associated with the key is a bunch of words that is contained in that document. Here are our map and reduce functions for this task. The map function takes in a document and first tokenizes its contents. Then for each word in the document, we emit an intermediate key value pair, with the key being the word itself and the value being just the number 1. Note that here we are not keeping any states inside the map function, so we can run this mapper across all the documents in parallel. Now, after the mapping phase is done, the system will group together all pairs that have the same word value together and pass that group to the reduce function shown here in the bottom right. Each reducer then goes through the list of values received, and for each one of those values, which is just the number 1, we sum all of those up. At the end, we just emit the word and the aggregated sum, and after collecting all of that information, we would have the word count for each word that shows up in that collection of documents. Here is how it works pictorially. We start in the mapping phase, where each thread reads in a document and produces an intermediate word value and the associated number 1. Then during the shuffle stage, we group together those key value pairs that share the same word, and each word will be associated with a list of the number 1s. And finally, during the reduce phase, we run our reducer on each of those groups of word and the counts, and we compute the final word count for each word and output them at the very end.